So the last type of bias what you are going to see is very, very important and commonly used biasing circuit called as voltage divider bias, or it is called as self bias, or it is called as emitter bias. So this is once this circuit was invented, this started ruling the world because this was found to be very, very effective against the variation in collector current. So it is a very, very simple circuit. It's a common emitter amplifier. You have a resistance, collector resistance RC and RE, and you have, I am going to add two biasing resistors R1 and R2. You can see this is the external circuit I'm going to add. I'm going to add resistance R1, R2 in such a way that R1 is between base and VCC, R2 is between base and ground. Okay, so this is the arrangement of the external biasing resistors. What I am going to add for this circuit is called as voltage divider bias, because you see this forms a potential divider, right? So R1, R2, VCC form a potential divider. So it divides the voltage VCC into two proportions depending on R1 and R2. If R1 and R2 are same, VCC by 2 will be appearing across both the resistors. But generally R1, R2 will not be same. While designing, I will say you what is the value of R1 and R2. But this is the arrangement for voltage divider bias. So this biasing circuit got its name by the virtue that the combination of R1, R2, VCC form an voltage divider circuit across the transistor. So it is called as voltage divider bias. And this circuit will establish a stable operating point that is guaranteed here. So this circuit is going to have a very stable operating point. That's why it is called as self-bias. So it will automatically fix the operating point in the correct position by itself when you properly design the values of R1, R2, RC and RE. Okay, while other circuits will exhibit variation in your collector current, this circuit was found to be very, very efficient. So it is also called as an emitter bias or emitter resistance. Potential divider can be used for low collector resistance as shown in the figure. So this figure shows the this figure shows the diagram for voltage divider bias, and analyzing the circuit using two resistance R1, R2 is very, very difficult. So what I will do, I will apply Thevenin's theorem across this point. I will apply Thevenin's theorem at this point. So when you apply Thevenin's theorem, you know you have to find R Thevenin and V Thevenin, correct? R Thevenin means excluding all the resistance what your circuit is having, you have to find the equivalent resistance. So when you find the Thevenin's resistance, you know you have to short circuit the voltage source. You see, I'm going to apply Thevenin's theorem. Everybody listen, this is very, very important. I'm going to apply Thevenin's theorem here. So you have to short the voltage source. So R2 is connected between VT and ground. R1 is connected between VT and VCC is now grounded. So what is the equivalent Thevenin resistance now? What is the Thevenin's resistance value? Can anybody say in terms of R1 and R2? Are R1 and R2 series or parallel? R1 and R2 are connected in series or parallel? I told you R2 is connected between VT and ground. R1 is connected between VT and ground. So what can you say about R1 and R2? R1 and R2 are series or
Series,
parallel?
sir.
Both are connected across the same point. So it is series or parallel?
Parallel.
Series, sir.
It is parallel, right? See, if you
Yeah,
redraw
but
the
both are
circuit,
grounded, right?
see where is R1? R1 is also connected here, right? So can you what R1 and R2 are lying to be parallel only, right? Same current will not flow through R1 and R2, right? Both are one end of both are connected to VT, other end of both are connected to ground. So if you apply a current here, it will divide equally into R1 and R2, correct? You're able to understand now?